also I'd like to thank my colleagues and friends for their help and support. I'd like to thank IAG of course, for providing me this great opportunity to deliver this lecture, to share my research with all of you. I'd like to thank all of you to come and to listen to my presentation. I'm very glad to attend this conference to celebrate the 60th anniversary of IAG. It's really wonderful. So the topic today is, can 2D fracture outcrops reveal a 3D population? Before I start, I have a brief introduction of myself. I'm Wei Zhu. I got my PhD in 2020 from King Abdullah University of Science and Technology in Saudi Arabia. And before that, I got my bachelor from China University of Petroleum, Beijing. And now I'm associate professor at the Institute of Geology and Geophysics, Chinese Academy of Sciences. And before that, I was a postdoc researcher and a research assistant professor at Tsinghua University. So now let's start this presentation. So from this title, can 2D fracture outcrop reveal a 3D population? From this title, at least you can summarize 3 keywords. The first one is fractures, which is the focus of my research and also the focus of this presentation. And the second one is from 2D to 3D. So we're concerned about multi-dimensional fractures and their correlations. And third one is population. This is a very important concept, and I would like to illustrate it further during my following presentation. So first, let's have a look at the very beautiful outcrop image from Brazil. This is collected by Professor Giovanni Bertotti from TU Delft. So as you can see, even for 2D outcrops, you can already observe those extreme complexities regarding fracture geometries and also intersection relationships. So, but the real fractures are not 2D, they are always 3-dimensional and in the subsurface, and they are very commonly observed in the subsurface as well. So why we care so much about fractures? That is because fractures are so important. Fractures are the very fundamental feature of the rock mass. So on the one hand, they are the failure plane of the rock mass. So it will affect or determine the rock stability, which were closely related to many mega constructions and also geohazards, such as landslides or earthquakes. On the other hand, they are also the highly permeable pathway for any kind of reflow in the subsurface. So they are so important for many engineering applications, including oil and gas exploitation, geothermal extraction, or the geological carbon sequestration, or the nuclear waste disposal, etc. So, do we know a lot of things about natural fractures? Unfortunately, no. We have very limited ways to know something about subsurface fracture networks, such as the seismic inversion, where you can see large-scale faults, an outcrop image, where you can see the fractures exposed on the surface, and all the wellbore images, where you can see the fractures intersecting the wellbore. But none of them can provide a complete picture of the subsurface fracture networks. So in general, the subsurface fracture networks is just like a black box. We do not know much about it. So among all the methods we have, the outcrop is the most abundant and widely spread data set we can easily collect. We can collect a lot of outcrops immediately with our phones, with UAV, or with any techniques you have. We can easily collect a lot of outcrops, but they may be different from the subsurface structures, because when the outcrops exposed on surface, you have upward movement, you have the stress release, you have weathering, you have a lot of things. It can make the surface and the subsurface totally different. But if the geological settings are similar regarding rock types or depositional environment are similar, we can infer some information from 3D fracture networks from the 2D outcrops. We can think these two items are related to each other, only when the geological settings are similar. So there's also challenges for outcrop observation, because it's easy to collect, but it's very difficult or tedious or time-consuming to interpret fractures from outcrops. For example, you want to have the fracture trace, you want to find the intensity, you want to find the length, orientation, topological structures, all those things. You cannot easily find that. If you do it manually, it will be very time-consuming. So you want to develop a better way to do it automatically. So we have done some research work in this methodology to automatically interpret fractures. So this technique will interpret the outcrop from the raw outcrop image to fracture traces, and then we can extract all the information we want. Sorry, I think there will be a timing. I need to move on. Sorry. So we developed an automatic fracture interpretation technology, which will interpret the fractures from the raw outcome image to fracture traces. Then we can extract all the information we want. So this technology will include two parts. The first one is fracture recognition, which will separate the fractures from its background. So it converts the outcrop map to a binary map, where all the fractures are shown in black and all the other things are shown in white. And the other part is the fracture detection. The binary image is not enough, we want the fracture traces. So the second part is to convert the binary fracture map to interpreted fracture maps, where all the fracture traces are tracked. So in-order learning is very powerful in recognizing patterns, and the fractures obvious is a very straightforward pattern to be recognized. So we use this deep learning technique to do the fracture recognition, but deep learning cannot do everything. For example, it cannot give us the trace directly. So it's also very challenging to obtain the coordinates of the fractures using deep learning techniques. So we still need to do our manual job. So we need to develop an automatic the fracture detection algorithm, and we have developed our own pixel-based fracture detection algorithm. So here we show the simple workflow for this method. This is a binary image where we can achieve from the deep learning technique. And then we convert it to a skeleton image, which is just 1 pixel wide image. And then we find all the initial and intersection points for pixels. Then we can track all the fracture traces. And here is marked in green and red because there are two types of it. The green type is constrained by at least one initial points, and the red one are constrained by 2 intersection points. So by doing this, anyway, we can automatically interpret the raw outcrop images to fracture traces. And then we can extract all the information we want, like the length distribution, the orientation distribution, or the topological structures. Everything we can just obtain it immediately, not just to do it with one map for one day, or that will be very time consuming, because I have done that. It takes me 7 days to interpret 7 outcrop. It's really very time. So with this technology, we automatically interpreted 80 outcrop maps from different parts of the world with scales varying from millimeters to tens of kilometers. I collected those outcrops from those publications since so we only use the fracture detection algorithm to interpret those fracture networks. And we found that 63 out of the 80 outcrop maps we have collected have formed a so-called spanning cluster, which are shown in red. These spanning clusters are those connected fractures, which also connect the boundaries of the domain. For here is all boundaries of the domain are all connected. So if in a system there is a spanning cluster forms, we call this system which is the so-called population status. So here is what I would like to illustrate the population status. It means the formation of the spanning cluster, which are the connected fractures which also connect the boundary of the domain. So the population status and the spanning cluster are very important because they are the key for the rock stability and also the seepage process, because they form the connected pathway. So from 2D outcrops, we can just visualize it with our eyes. But how about the subsurface? Can we infer anything about the population status of the subsurface fracture networks in 3D? It's very difficult, because to infer something from 2D to 3D is a highly undetermined inverse problem. So the solution cannot be unique. So we need to change our mind, to change our logic. So if we can generate 3D fracture networks first, and then we can cut the 3D fracture networks to get the cross-section map, which is used to mimic the outcrop images. Because the outcrop is also a cross-section map with the surface as a cutting face, right? So if we do so, we can convert this problem into a determined forward problem. So we can know everything about the 3D fraction networks and also 2D fraction networks, and then we want to try, to find the correlations between these two items. So our idea is that we can generate various 3D fraction networks to represent the actual fraction networks in the subsurface. But as I mentioned before, the subsurface is like a black box. How we can do that? We do it with a method called discrete fraction network method, and then we can generate 3D fraction networks. So for people who are not very familiar with discrete fraction network method, here is a brief introduction. So this method is to explicitly represent geometric property of individual fractures, which usually includes the fracture orientations, sizes, positions, shapes, and also apertures. So in 2D, it's very simple. We just use a line segment to represent fractures. But for 3D, we have different options. We have round disk, or we have disk shape, or elliptical disk shape, or any random polygon shapes. You can choose different shapes to represent your 3D fractures, but it's still a significant simplification of the actual fractures. Because actual fractures, you have roughness, you have curved structures, and you have a lot of complexities. But you cannot characterize it in too much details. Then it will be very impossible. And then you also have different sources where you can generate discrete fraction networks. First one is geologically mapped fractures, where you can map all the fractures you observe from the outcrops or tunnels or road cuts. And then you will have your DFM. A second way is that the geomechanical simulation, where you need to simulate the nucleation, propagation, and pliescence of discrete fractures. And this process will be very time-consuming and not very widely used. And also you need to simplify the problem by using linear elastic fraction mechanics. And third one is stochastic degenerate fraction networks, where we use different distributions, statistical distributions, to characterize the fracture geometries. For example, its length, positions, and also orientations. I would like to further introduce what kind of distributions we can use. So for the fracture length, a lot of geologists have proposed a lot of distributions to describe the fracture length, like the exponential, gamma, log normal, and power law distribution. And among those distributions, the power law distribution is the most dominant distribution used to describe the fracture length. And I also have derived that the origin of this power law distribution. That's because fractures are usually regarded as similar structures. It means you can observe similar patterns at different scales. So if you consider that the large fractures are the results of the quiescence of small fractures, and then you will derive the length distribution, and you will follow a power law distribution. I have done that derivation. And also the orientation, which people always use the von Mises-Fischer distribution to describe the orientation, which is constrained by two parameters. One is the mean direction mu, and the other one is the concentration degree kappa. So this kappa value will decide how concentrated is the orientation. If the kappa is very small, like this red one, then it's just close to the uniform orientation. If it's very large, like the green one, then it will be very concentrated. If it's zero, then it becomes just a uniform distribution on this ball. And for the position, people use uniform spatial density distribution, or more generally, we use fractal spatial density distribution. This is characterized by so-called fractal dimension in this case. In 2D scenarios, if the fractal dimension is 2, then the distribution will just become a uniformly spatial distribution. If it's smaller than 2, then there will be clustering effects. And same thing in the 3D. If the fractal dimension is 3, then it's just uniformly distributed. If it's smaller than 3, then there will be clustering effects. And from the outcrop observations, we found that the clustering effects are very commonly observed in reality. So fractures used to cluster together, not just uniformly distributed. And so with this method, we can generate various 3D fraction networks with the discrete fraction network method. And here is the geometric parameters we considered, the fracture length, positions, and also orientations. We use the widely used distribution to describe those geometries. And then we use different parameters to generate different scenarios. And here for the orientation, we just use one number, which is 0, which means we consider about the uniform distributed fractures first, and then we will consider more complex fraction networks with more preferential orientations. And here the system size is to account for the finite size effect, because the classic population theory will deal with the systems with infinitely large size. But all the systems we generated always have a finite size. So we have used different system size to account for the system size, finite size effect. So in total, we have generated 440 scenarios of 3D fraction networks. And since they are all stochastic processes, so the results cannot be stable. If we want to make the results stable, we need to stabilize the results with multiple iterations. So in our case, we for each scenario, we will stabilize it with 50 iterations. So in total, we will have 22,000 3D realizations. So in this case, if we want to find the spanning cluster, we need to run the cluster check algorithm for millions of times. It is very time-consuming, and we need a very powerful software to do that. And we have done this. We developed a very efficient DFN modeling software named HashFrac. And this is a 3D fraction networks demonstration generated by HashFrac. And this is a time-consuming to generate this number of fractures. So compared with the highly cited open source software ADFNE, our software is very efficient. So we generate 100,000 fractures in 3D. We only need 3 seconds, but they need 6 minutes. So the efficiency improvement is more than 120 times, which is very significant and enable us to do the investigation on this project. And we have published this work on computers and geotechnics. It's open source. If you are interested, you can always download it to use. But unfortunately, it's not very user-friendly, so if you have some troubles, just contact me. And then, here we are. We can start this project. We generate 3D fraction network first, and then we cut it. We use a cross-section to represent the outcrop. And we can see the 2 phases here. Well, the first phase is a spanning cluster formed in the 3D fraction networks, as this one, as shown in red one. And the second phase is that a spanning cluster formed in 2D cross-section maps, like this one. This is what we observe from most outcrop images. So you may argue why you choose the middle position to cut it. It will have a little slight difference if you choose different positions, but it will not influence the results significantly. So we consider these 2 phases, and then let's come to the result. So in this result, actually you can find a lot of interesting things, because you have generated 3D fraction networks and with very wide variations, and also you have all the 2D informations. You can find a lot of interesting correlations. But here I just summarize the most important results from this investigation, because we focus more on the formation of the population clusters, the spanning clusters. So if there is no spanning cluster formed into the outcrops, like the phase 1, as you can see here, there's no spanning cluster on the outcrops, but there are already a spanning cluster formed in the 3D fraction networks. So it means even you see that the fractures are very sparse on the surface, it doesn't mean that the subsurface fraction networks are also sparse. So if the fraction intensity is large enough, then there's still a possibility that the 3D fraction networks can be formed in 3D. So how we can find this criteria? So we use the number ratio to indicate that, which is the number of the 2D fractures at the phase 1, which is the unpopulated status, and over the number of 2D fractures at phase 2, a populated status. So for these 440 cases, we find that the maximum value is 0.43. It means that if the outcrop maps have this fraction intensity larger than 43% of the fraction intensity required to form a spanning cluster, then there is a very high chance that 3D fraction networks already form a spanning cluster. So you may argue that in this case we know this number, but from real outcrop you will never know what is the number of fractures at the population status. So that's why you need to summarize the distributions of your outcrop observation. To summarize this distribution for the length, orientations, and positions, and then to distribute more fractures until it reaches the population status. And then you can find this number. You can try it for many times and see whether this value will change or not, a lot. If not, then you will have a much stable result. Also, here the fraction intensity, we use the number ratio. You can also use the other indicators, but it will not change the result a lot. For example, you can also use the length ratio, which is the length of the fracture at phase 1, the total length of fractures at phase 1, and over the total length of fractures at phase 2. And the maximum value is 0.441. It doesn't change a lot. So generally, the trend will not change, a little bit change on the specific values. And for the second phase, where the spanning cluster already forms in 2D outcrops, like this one, this is what we observed in most outcrop images. Then the corresponding 3D fraction networks will be overpopulated, which means the fraction intensity is much higher than the fraction intensity required to form the spanning cluster. We also use the number ratio to indicate how high the fraction intensity will be. So this is the number ratio, which is the ratio between the number of 3D fractures at phase 2, overpopulated status, and the phase 1, populated status. And for these 440 cases we consider, we find that the minimum number is 3.5. It means that if there is a spanning cluster formed in the 2D outcrops, then the corresponding 3D fraction networks will be overpopulated, and this fraction intensity will be at least 3.5 times larger than the fraction intensity required to form the spanning cluster. And we also consider the fracture networks with more preferential orientations composed of multiple fracture sets. So compared with this cross-section map and this outcrop map, you may see they looks a little bit, they are not identical, but they share some similar features, such as different fracture sets and the preferential trends. So in these complex fracture networks, we also see that the number ratio of the corresponding fracture networks is 15.5. It's consistent with the result we observe, and the 3D fracture networks should be overpopulated. So with those important results we get, we can try to answer this question. Can 2D fracture outcrop reveal 3D population? The simple answer is yes, we can. We can review some 3D population information from 2D outcrop maps. But the more complex answer will depend on the fracture intensity. So if there is no spanning cluster formed in 2D outcrop maps, but the fracture intensity in 2D is large enough, then there is still a possibility that the spanning cluster may form in corresponding 3D fracture networks. And we also give you the number, which is 43% of the intensity required to form a spanning cluster. And if there is a spanning cluster already formed in the 2D outcrop maps, then the corresponding 3D fracture networks must be overpopulated. And we also give you a quantity that the intensity should be at least 3.5 times larger than the intensity required to form a spanning cluster. So now, this subsurface fracture networks is not a complete black box to us, because we can know something. The most important characteristics of these 3D fracture networks is population status from the observation of 2D outcrops. And we have published this paper in engineering geology, and this work has greatly deepened our understanding of the subsurface structures, subsurface fracture networks. And here I only show the fracture intensity, but you can also to have a look at my original paper, and where you can find the intersections and the connectivities. You can find many other interesting indicators about multidimensional fractures. So it has greatly deepened our understanding of the fracture networks in the subsurface, and which also serve as a foundation of my further research work. So based on the insights we gained from this research work about the population status, we can further quantify the connectivity of complex fracture networks. So here we show the fracture networks, and we can see the different colors represent for different clusters. The usually complex fracture networks are composed of multiple clusters which are connected by permeable matrix. It's very difficult to quantify the connectivity in such complex systems, and we have proposed a very novel indicators to do that, which account for the individual contributions for each individual cluster, and also account for the interactions between different clusters. By doing this, we can quantify the connectivity of complex fracture networks it can also extend it to 3D. Here I only show 2D because it's for better visualization. For 3D, then it will be very hard to plot it and also to visualize it. So why we need the quantification? Because we want to investigate the influence of the fracture, influential factors for the connectivity. Connectivity is very important property for the fracture networks. So with the quantification, we can quantify the influential factor. For example, the fracture thinning. If you have, this is a very well connected fracture network. If you consider all the fractures are open, then it will have very good connectivity, like this. But if you have some fractures are sealed by the cements, all the apertures are reduced by the compressive node, and then it will be a totally different case. If you just randomly distribute the fracture thinning in these fracture networks, just 5% of it, you will divide this fracture network into multiple local clusters, and the connectivity will be significantly reduced. This is uniform distributed fracture thinning. If you intentionally to seal some very critical fractures, for example, the linkage fractures between different clusters, then it will have much more significant impact on the connectivity. It's very important. For example, it can help us to optimize artificial fracture filling to prevent landslides, the grouting process. If we can find those critical fractures and seal it, and then it will significantly reduce the connectivity of the overall fracture networks. And furthermore, we can also characterize the dynamic evolution of the fractures under artificial influence. For example, the hydronic fracturing process. We have known much better about the subsurface fracture networks from this research work, so we can always try to construct much more complex and realistic rock mass models with the discrete fracture network method. And then we also developed a very advanced discrete element and lattice Boltzmann method to simulate the hydraulic fracturing process. So we can systematically to investigate how the fractures will initiate and how they will propagate and how they will form the complex fracture networks in those very complex heterogeneous rock mass. It will tell us a lot of information about this dynamic process. And more importantly, with the quantification of connectivity, we can quantify how the fracture evolved and how the connectivity evolved during this hydraulic fracturing process. And so this research work is very important, and it has very significant research impact, which also leads to many more publications in recent years. Actually, in recent 3 years, it has led to more than 10 publications. And those publications are published in very prestigious journals in geoscience, such as Nature Index Journal, Geophysics Research Letters, and also Journal of Geophysics Research Solid Earth. We also have publications in engineering geology and also computers and geotechnics, etc. So I think on this, it's almost half an hour. I think on this note, I should stop here. We have proposed a methodology where we can infer 3D information from available 2D informations. And we reverse our logic from the inverse problem to the forward problem, which will help us to understand the subsurface fracture networks much better. And I would like to thank my collaborators from different institutions, and also to thank the IAG and the jury and the YEG, the C29, and also the China National Group. So thank you very much. I think that's all. You are very welcome to ask questions if you have any. Thank you.
Yeah, thank you very much. Well, thank you for being on time. So I see questions. Okay.
Thank you very much. I have 3 small questions. The first one is, are all fracture distributions mechanically possible, therefore related to a stress tensor, even if we consider a stress tensor evolving in time, explaining what we have today when we're looking at the no-crop? But is there a sort of mechanical control on the result of a software that seems a bit statistically based and nothing else? Am I correct in this?
Thank you for the question. It's a very good question. Of course, the fracture's formation and its propagation will depend on the stress, but that is the cause why the fracture will propagate in this way. When we model the fractures, actually we look at the result. So that's why those distributions are summarized from the existing fracture networks. We can incorporate the physics in these discrete fracture network models, but not directly incorporate those physics law. Then that will become a very direct numeric simulation. That is a totally different case because it will be very time consuming and you will never consider thousands of fractures or millions of fractures if you do that way. So the way we do is that we will summarize those physics results, how those physics will influence the fracture geometries, and what's the result of it. We will summarize these kind of things and to some rules or what kind of things we can easily implement it in the discrete fracture group. That's how it works. I hope this answers.
Is there a theoretical study of the possibility or not possibility of an existing network of fractures? Are there cases that cannot be possible in nature that your software can simulate? You see what I mean?
I understand your problem. Your question is how to validate the results, right? Yes, that's a very good question, and always it's very difficult how to validate your results. But unfortunately, no, because the subsurface we do not know all the details of the subsurface fracture networks. So you can have partial information, you can have some point validations, you can have some cross-section validations, but you cannot have a 3D validation in very detailed. That's a problem, and that's always a problem because it's a black box. We cannot solve this black box, and that's why we need to find some way to understand this black box much better. It's just like elephant in a room. You will not see the full picture. Yes, it's very difficult to validate in a very detailed way. Yeah, I think that's my answer.
Okay, thanks. The second question, if I can. Are the fractures defined with a thickness in your models?
Which one you consider about thickness?
Because when we see your pictures, we've got planes everywhere, but from a mathematical point of view, they're located somewhere in space, they have an orientation, but do they have a thickness, and how do you define it?
For 2D fractures, they do not have thickness. We only consider about the length. And sometimes we can consider about the aperture. I'm not sure whether your thickness is equal to the aperture I'm discussing about.
Yes.
Okay, yes, we can consider about the aperture in discrete fracture networks. For 2D, it's simple. You just divide your very long fractures into very small segments, and then you can assign different apertures to your fractures, and then you can consider your impact of apertures in kind of ways, not very accurate, but you can consider about apertures. And in 3D, the same case. You can divide your 3D fractures into small blocks, and then to assign the apertures to do that. It's doable. And we have done some research on that as well.
And have you studied the sensitivity of the results on the thickness of your fractures?
It depends. It depends what kind of problem you want to test. If you want to test the probability, then of course it will influence a lot. But if you just want to say its connectivity, because why fractures are important is compared with the matrix. If the matrix is very low probability, then fractures will play a very important role, right? If the matrix is kind of also very high probability, then the fractures will not be that important. So the apertures will also have a relative comparison with the matrix and with the other fractures. It depends what kind of problem you want to investigate. Of course, in some cases it will be very sensitive, but in some cases it will not. It depends on the target, yes.
And the last very short question is about the input.
Yeah.
You're basing your analysis on photos, am I correct? So do you consider that all cracks, all fractures can be detected by photos? Are they all visible?
You mean the small fractures?
Because if the thickness is very narrow, you won't see them, and you won't be able to detect what's going on.
Yeah, exactly. That's why I do not extract aperture information from the fracture outcrop images, because it's not that trustworthy. After a very long geological time, the weathering and everything, I don't think the apertures nowadays can represent the apertures of the real fracture works. So the fracture aperture will also be described by a distribution, actually, not by the measurement from the polygon.
There was another question.
Thank you.
Helen, please.
Hi, thank you very much for a fascinating talk. In industry, WSP Golder's Fracman software is kind of one of the industry standards.
Yeah.
How does your software compare with that, and have you used that to help with some of the calibration?
Yes, I had the software. I have used the software Fracman when I was a PhD student because cost is very rich and they buy the license for that software. And to be honest, it's not cheap. And we tried to compare some results, the efficiencies of my software and their and his software. My software is a little bit faster, but their functionalities is much more than my software. But it's still, the advantage is that I know everything about my software, but I don't know anything about their software. So I cannot, for example, I have some very specific requirements. I need to contact that technician to solve it for me, but for me, I can solve it by myself. That's the advantage why we want to develop our own software. Yes.
Any other question? I was almost sure that Fred would have a question. No?